sorry for being late. I'm really late. The reason is I went and got myself, not got, like made myself coffee. So sorry about that. And sorry for keeping you waiting. I hope you went and no. I hope you also have some beverage because we're gonna be here a while. Okay, so let's start. Good morning, good before noon, good afternoon, good evening, and if it's good night, then good night. Let's start with a wrap up. Hello, Mustafa. Thank you for being here. Okay. Where is the screen? Right behind me. Thank you. So we are in lesson 3 in the, each time I feel like starting with thank you. This is a Friday outfit. The beads move when no, they don't? Oh yeah, they do, but they also go into my body, which is not a good thing. Yes, Introduction to Machine Learning for Coders from fast.ai. This is what we're doing. And we are in lesson 3, lesson 1 and 2. We're intro to random forest and a deep dive on random forest, and lesson 3 is we're still working with random forest, but we are looking at performance validation and model interpretation. So this is the thing with the lesson 3, but we're watching it on YouTube. We were just starting with right here it says break, so it's break time for them. That's where we finished, and we actually, this is lesson 1, this is lesson 2. We have lesson 2. I won't start with the code because I know when I do I will have a problem, so let's start when we need to start. Maybe we already need to, but let's see. I know I'll have problem with the feather thing because I don't have it in my, like, if I run this, hopefully the person already, let's see if the person already has the feather, because if they do, then that would be great. Seems like it's still the blue book for bulldozers, not the feather thing. Maybe the person actually made it. Yeah, see, they made it that loading from our last lesson. Okay, people are good, people are nice. That's great. Okay, maybe you won't have a problem, but I'll start off with what are we doing? My God, why are people here? Like, I'm surprised people are here on a Friday in this economy. Okay, I'll play this and let me know if you need anything. And I think my mic is working. Yes, because I've had issues where it wasn't. Do I need to change my hijab color? Is the black too one color with the background? Because I have a really cute pink one, but I thought wearing all pink would be really weird. I think there's a white one, but it doesn't go with the style. There it is. There's this really cute pink one. Yep. Okay. Let's study. We're here to learn. I'm gonna...
And that I had in my test set, for example.
And then
okay, let's take a 5-minute break and let's come back at 2:32.
Oh, they're back? Or is it still break time for them?
Okay, so this is my favorite bit, interpreting machine learning models. And by the way, if you're looking for my notebook about the groceries competition, you won't find it in GitHub because I'm not allowed to.
Thank you. Thank you. I can see my mic moving. Otherwise, it wouldn't move if it wasn't working.
Share code for running competitions with you unless you're on the same team as me. That's the rule. After the competition is finished, it'll be on GitHub, however, so if you're doing this through the video, you should be able to find it. So let's start by reading in our feather file. So our feather file is exactly the same as our CSV file. This is for our Blue Book for Bulldozers competition. So we're trying to predict the sale price of heavy industrial equipment at auction. And so reading the feather format file means that we've already read in the CSV.
Not for my eyes, at least. I'd like to see an old pink outfit. Nothing wrong with about that. Thank you. It would be mostly a fashion crime, not me thinking it's rude. I like all colors, and I wear colors based on you know how one person is feeling. So sometimes you're feeling pink, sometimes you're feeling black, and that's okay. Thank you though. So I think we're starting with actually running things. I should copy and edit this lesson 2. Because he's saying, let's start with loading things.
And processed it into categories.
And I actually encourage whoever's watching to do this. Let's do this together so that we can face issues together. I can even send the link to the thing. Wait. I will do this. Look at my history so that I can send you the link. Let's go back to history. Okay, here it is. Lesson 2. This guy's, lesson 2. I'll put it in the chat in case. You also want to join. Here's my version. Okay, it's going.
And so the next thing we do is to run procdf in order to turn the categories into integers, deal with the missing values, and pull out the dependent variable. Okay. This is exactly the same thing as we used last time to create a validation set, where the validation set represents the last couple of weeks, the last 12,000 records by date. And I discovered, thanks to one of your excellent questions on the forum last week, I had a bug here, which is that procdf was shuffling the order. Sorry, not procdf. And last week we saw a particular version of procdf where we passed in a subset. And when I
having problems with the categories in validation or test set not being in the training set. That was the issue he talked about last time.
Passed in the subset, it was randomly shuffling, and so then when I said split vals, it wasn't getting the last rows by date, but it was getting a random set of rows. So I've now fixed that. So if you rerun the lesson 1 RF code, you'll see slightly different results. Specifically, you'll see in that section that my validation set results look less good, but that's only for this tiny little bit where I had subset equals set. Yes, Chenchi.
I'm a little bit confused about the notation here. So NAS is both a input variable and it's also
literally same question. Like, why is NAs coming out and going in? And because we don't have it before. Thank you. I love these students.
The output variable of this function. And why is that?
The procdf.
And he's still in the lesson 1 file, even though he went to lesson 2 yesterday. Okay.
Returns a dictionary telling you which things were missing, which columns were missing, and for each of those columns what the median was. So when you call it on like the larger data set, the non-subset, you want to take that return value, right? And you don't pass in an NADIC to that point. You just want to get back the result. Later on, when you pass it into a subset, you want to have the same missing columns and the same medians, and so you pass it in. And if like this different subset, like if it was a whole different data set, turned out it had some different missing columns, it would update that dictionary with additional key values as well. So it kind of, you don't have to pass it in. If you don't pass it in, then it just gives you the information about what was missing and the medians. If you do pass it in, it uses that information for any missing columns that are there, and if there are some new missing columns, it'll update that dictionary with that additional information.
So it's like keeping all data sets, column information.
Yeah, it's going to keep track of all any missing columns that you came across in anything you passed to procdf.
So the NAs here can go back in because they said you can give it or not, and we're giving it a list of like the NA dictionary, so it's how many NAs we have, so that procdf knows it, and we can check what procdf does with the NA dictionary. Should we? I'm thinking, because then I'll have to run the whole thing because I've been neglecting lesson 1. I mean, you'd have to run the whole thing to come to this part. Let's see if we can. Where's the speeding things up header? Bagging there, here. So you have to say run before and then just give it 5 minutes, right?
Thank you.
Okay, so we split it into the training and test set just like we did last week. And so to remind you,
now we're in
once
lesson
we've
2.
done procdf, this is what it looks like. This is the log of sale price. Okay. So the first thing to think about is we already know how to get the predictions, right? Which is we take the average value in each leaf node in each tree after running a particular row through each tree, right? That's how we get the prediction.
Okay.
But normally we don't just want a prediction, we also want to know how confident we are of that prediction. And so we would be less confident of a prediction if we haven't seen many examples of rows like this one. And if we haven't seen many examples of rows like this one, then we wouldn't expect any of the trees to kind of have a path through which is really designed to help us predict that row. And so conceptually, you would expect then that as you pass this unusual row through different trees, it's kind of going to end up in very different places. So in other words, rather than just taking the mean of the predictions of the trees and saying that's our prediction, what if we took the standard deviation of the predictions of the trees? So the standard deviation of the predictions of the trees, if that's high, it means each tree is giving us a very different estimate of this row's prediction. So if this was a really common kind of row, right, then the trees will have learnt to make good predictions for it because it's seen lots of opportunities to split based on those kinds of rows.
Okay.
Right? So the standard deviation of the predictions across the trees gives us some kind of at least relative understanding of how confident we are of this prediction. So,
okay, sure. Mean or standard deviation, why not?
that is not something which exists in scikit-learn or in any library I know of. So we have to create it. But we already have almost the exact code we need, because remember last lesson we actually manually calculated the averages across different sets of trees. So we can do exactly the same thing to calculate the standard deviations. So when I'm doing random forest interpretation, I pretty much never use the full data set. I always call set RF samples, because we don't need a massively accurate random forest. We just need one which indicates the nature of the relationships involved, right? And so I just make sure this number is high enough that if I call the same interpretation commands multiple times, I don't get different results back each time. That's like the rule of thumb about how big does it need to be, right? But in practice, 50,000 is a high number, and most of the time, it would be surprising if that wasn't enough, right? And it runs in seconds. So I generally start with 50,000. So with my 50,000...
Good rule of thumb. I like how each time he's starting, just understanding the data by playing with it, and then when he's confident with what he's doing, then he works with the whole data. And obviously it's all training data, so it's okay. It should be fine. Lesson 2. We ran this. We have a warning. Yes, it's a warning. We are setting the plot size, loading the data from lesson 1. Still warning. I hope everything's fine. How nice, the person is bringing lesson 1 here. And then getting the split vowels, defining that. And then, okay, RMSE, print score, looking at DFRA, hello. We haven't done the procdf yet, so we should see, yes, NAs and text and everything. That's way too much. I should have said head. Okay, now we are doing the 50,000, and we'll stop here right exactly where he is.
Samples per tree set. I create 40 estimators. I know from last time that min samples leaf equals 3.
By estimators, we mean trees. Okay. Min sample leaf equals 3, he said.
I create 40 estimators. I know from last time that min samples leaf equals 3, max features equals 0.5 isn't bad. And again, we're not trying to create the world's most predictive tree anyway. So that all sounds fine. We get an R squared on the validation set of 0.89. Again, we don't particularly care, but as long as it's good enough, which it certainly is.
We have a score. We don't care. That's cute. Let's print our score. That should take a minute. I'm gonna... Are you still running? You shouldn't be. 6 minutes. Where is it? There's been an error, because I remember saying, yes, there's an error. which is normal. There should be an error, right? No? There is one where it's like you should be getting an error. Yes, you're actually true. Competitions and hackathon spirit, where you're like, it's fine. I have something that I can submit. Let's go. That's lesson 2. Yes. Oh, okay. Yeah, we have a score. We don't care. Let's go. 24 for the test. 88. I mean, not test validation. Literally same. Yeah. Because I mean, I've talked about it 1,000 times. I'll say it again. In my first hash code, I didn't even know how to submit because I wasn't prepared. So I got 0. Like, normally you never get 0 in hash code because you can always submit the sample thing, but I got 0. So having something to show to the jury is better than nothing.
And so here's where we can do that exact same list comprehension as last time. Remember? Go through each estimator, that's each tree, call .predict on it with our validation set, make that a list comprehension, and pass that to np.stack, which concatenates everything.
I got none of that. I was drinking coffee. Let's go back. Sorry.
Do that exact same list comprehension as last time, remember?
Great. Good. That's great. I did Code Jam once and I didn't really go through, but yeah. It's fine. Like, honestly, it's fine starting with nothing. Like, you can just jump into an ocean. I'm talking not about literal oceans. I'm talking about coding. You can jump in head first and you'll fail, and that's okay. And then you'll learn from your mistake, hopefully.
Go through each estimator, that's each tree, call .predict on it with our validation set, make that a list comprehension, and pass that to np.stack, which concatenates everything in that list across a new axis. Okay. So now our rows are the results of each tree, and our columns are the result of each row in the original data set. And then we remember we can calculate the mean, right? So here's the prediction for our data set row number 1. And here's our standard deviation.
Cool.
Okay, so here's how to do it for just one.
That was cool. Yes. I like failing in safe environments, not in production environments. Yeah, like, that's what I love about school. You can fail safely. Even this, I can fail. No worries. Let's look at our standard deviation. I'm going to read this so that I understand what he's saying, because sometimes I don't. Oh, our standard deviation is different from his. His is lower, 0.21. Mine is 0.28. We saw how the model averages predictions across the trees to get an estimate. Yes, that's what we did in lesson 1. But how can we know the confidence of the estimate? One simple way is to use the standard deviation of predictions instead of just the mean. This tells us the I think, like, we're talking about performance now, right? And, like, I know about what is the thing? Accuracy, and then what is the other thing? There's another thing. Yeah, F1 scores and stuff like that. But, like, we're starting off with things that make sense for a human brain. Like, looking at the mean, and then this one's standard deviation. This tells us the relative confidence of the prediction. That is for rows where the tree gives very different results. You would want to be cautious of using those results compared to cases where they're more consistent. Okay, using the same example as last time when we looked at bagging. Yeah, with the estimators and the leaves and the features and the OOB score. Yeah. Okay. Now what? Now what do we do?
One observation at the end here. We've calculated for all of them, just printing it for one here. Now, this can take quite a while, and specifically, it's not taking advantage of the fact that my computer has lots of cores in it. List comprehensions. This is like the list comprehension itself is Python code, right? It's my Python code, and Python code, unless you're doing special stuff, runs in serial, which means it runs on a single CPU. It doesn't take advantage of your multi-CPU hardware. And so if I wanted to run this, on more trees and more data, this 1 second is going to go up. And you see here the wall time, the amount of actual time it took, is roughly equal to the CPU time.
Oh,
whereas if it was running on lots of cores, the CPU time would be higher than the wall time.
So you're calling this slow? The 1 second thing? Oh wow, look, mine is 3. He's calling this slow? I thought it would be like minutes.
So it turns out that scikit-learn provides a handy, actually not scikit-learn, fast.ai provides a handy function called parallel trees, which calls some stuff inside scikit-learn. And parallel trees takes two things. It takes a random forest model that I trained, here it is, M, and some function to call. And it calls that function on every tree in parallel. So in other words, rather than calling t.predict xvalid, let's create a function that calls t.predict xvalid. Let's use parallel trees to call it on our model for every tree. Okay, and it will return a list of the result of applying that function to every tree.
That function on every tree. Instead of us looping on the tree, there's a parallel way? Okay, because I think we were... Okay, yeah, see, we were using a for loop here. Yes, I think, okay.
And so then we can np.stack that. So hopefully you can see that that code and that code are basically the same thing.
But better?
Right? But this one is doing it in parallel. And so you can see here now our wall time has gone down to 500.
Whoa, that's cool. Let me try. Let's look at my wall time, because... Wow, look at that. Look at the CPU time. 미쳤다. Wow. Which means that's crazy. Okay.
100 milliseconds, and it's now giving us exactly the same answer. Okay, so a little bit faster. Time permitting, we'll talk about...
Exact same answer, as it should be. Yes, exact same answer. So cool.
More general ways of writing code that runs in parallel, because it turns out to be super useful for data science. But here's one that we can use that's very specific to random forests. Okay, so what we can now do is we can always call this to get our predictions for each tree, and then we can call standard deviation to then get them for every row. And so let's try using that. So what I could do is let's create a copy of our data, and let's add an additional column to it, which is the standard deviation of the predictions across the first axis. Okay?
And what we are predicting is the sales price, by the way. Like this is what the new column should be, right? Yes. That's what we're checking for standard deviation and the mean, what we were doing last time, right?
And let's also add in the mean, so they're the predictions themselves. So you might remember from last lesson that one of the predictors we have is called enclosure, and we'll see later on that this is an important predictor. And so let's start by just doing a histogram. So one of the nice things in Pandas is it's got built-in plotting capabilities. It's well worth Googling for Pandas plotting to see how to do it. Yes, Terence?
Jeremy, can you remind me what enclosure is?
That's nice. I don't know what an enclosure is, but it feels like what is it called? It reminds me of encapsulation for some reason.
We don't know what it means, and it doesn't matter. Like that's the whole purpose of this process, is that we're going to figure out, we're going to learn about what things are, or at least what things are important,
by
and
using
we'll later
them?
on figure out what they are and how they're important. So we're going to start out knowing nothing about this data set, right? So there's something, so I'm just going to look at something called enclosure that has something called eRops and something called ORops, and I don't even know what this is yet.
Same.
All I know is that the only three that really appear in any great quantity are ORops,
Love it. I'm really enjoying this environment that they're creating here.
eRops, WAC, and eRops. And this is like really common as a data scientist. You often find yourself looking at data that you're not that familiar with, and you've got to figure out at least like which bits to study more carefully and which bits seem to matter and so forth. So in this
Hello to you too, sir. I wouldn't call myself a sir, but thank you. Welcome. We are learning here. How can I call you? Is Chotu okay, or is the V also a part of your name?
case, I at least know that these three groups I really don't care about because they basically don't exist.
Yes, they don't.
So given that, we're going to ignore those three. So we're going to focus on this one here, and this one here. And so here you can see what I've done is I've taken my data frame and I've grouped by.
Okay, welcome. We're studying Fast AI's Intro to Machine Learning for Coders. And we're in lesson 3. Do you have any info about the Fast AI courses? Because they have a lot. And yesterday when he was talking about Jeremy Howard, the instructor, was talking about Kaggle competitions, and he said that I think it was like the 3rd place one using deep learning without feature engineering. Did I mess something up? I think I messed something up. Sorry. And that made me be like, I should jump to deep learning after this intro to machine learning. I don't know though, but that would be cool. No, I am not. I am not an AI. I am we call this style VTuber, VTuber, where you are behind a character and the character is tracing my face. So when I'm talking, it looks like the character is talking. Yeah, it's a virtual thing. VTube means virtual YouTuber, by the way. I think, right? Because even Twitch people are called VTubers. I am a human. Yes. God, that's weird. It's the first time I've been asked if I'm a human or not. Okay. But indeed I am a human. That would be cool, yeah. If I am not trusted. Okay. I am a human who makes videos on YouTube and does lives. So I guess you can check my videos to see that I am a human. Okay. Let me know if you have any questions. I am a person who likes computer science and tech things and likes studying. Are you AI, Mr. Chotu?
And so here you can see what I've done is I've taken my data frame and I've grouped by enclosure, and I am taking the average of these 3 fields. So here you can see here's the average sale price, the average prediction, and the standard deviation of prediction for each of my 3 groups. Mm-hmm. So I can already start to learn a bit here.
Is this the mean? This is the mean, and then this is standard deviation, but for these things, which we really don't know what these are.
As you would expect, the prediction and the sale price are close to each other on average, so that's a good sign. And then the standard deviation varies a little bit. It's a little hard to see in a table, so what we could do is we could try to start like printing these things out. So here we've got the sale price for each level of enclosure, and here we've got the prediction for each level of enclosure, and for the error bars I'm using the standard deviation of prediction.
Cool. I'm gonna test that on my notebook, making a copy, doing, ooh, mine is colorful, his wasn't, mine is better. We have these things which we have no idea what they are, and we're not gonna check because students are lazy, and I am right now a student of this class. And then we are looking at the table of standard deviation and then the predictions of the things. These are nouns. I see these 2. Okay, here's the other noun. Got it. And nouns are not the thing you eat. They are not a number. That's what it stands for. And then, I don't know why I keep reading this as bra instead of bar H. And then we're looking at these lovely colorful things. These 2 colors go together well. These 2 colors go together well. Yes, this is fashion. And we are looking at the error bar. Error bar. Cool. Nice. I was able to click all the buttons. I'm proud of myself.
Right, so here you can see the actual, and here's the prediction, and here's my confidence interval. Okay.
Confidence interval. Okay.
Or at least it's the average of the standard deviation of the random forests.
Okay.
So this tells us, it'll tell us if there's some groups or some rows that we're not very confident of at all. So we could do something similar for product size, right? So here's different product sizes. We can do exactly the same thing of looking at our predictions and our standard deviations. Okay, we could sort by, and what we could say is like, well, what's the ratio of the standard deviation of the predictions to the predictions themselves, right? So you would kind of expect.
We're still talking about sales price, but per product size. To see what's the difference per product size. Okay.
On average, that when you're predicting something that's a bigger number, that your standard deviation would be higher, right? So you can like sort by that ratio. And what that tells us is that the product size large and product size compact, our predictions are less accurate.
This is how much it's deviated. Okay, but they're pretty close to prediction style. Let's look at mine. I don't know why mine is different, because like in decision trees you should get the same answer. It's not like a black box. Is this, what are we doing? How value count, product size value count, that's it. Why are predictions nearly exactly right, but the error bars are quite wide? This is not an error bar, is it? Not yet. Shouldn't be. Okay. Huh. Large and... Was it large and compact, or was it large and medium? Compact. Large has a way bigger standard deviation for me. Even that one, small. This one has the best standard deviation because it's a mini. Okay.
As relatively speaking, as a ratio of the total price. And so then if we go back and have a look, well, there you go. That's why. From the histogram, those are the smallest groups.
Yeah, we're checking how much data we have. But mini isn't the biggest. Medium is. And medium has an okay standard deviation, but compared to these two, like, the difference is negligible, but I don't know if it's negligible, but I just felt like using that word, yes. Okay. Sorry. Let's continue.
Okay, so as you would expect, in small groups, we're doing a less good job, right? So this confidence interval you can really use for two main purposes. One is that you can group it up like this and look at the average confidence interval by group to find out, are there some groups that you just don't seem to have confidence about those groups? But perhaps more importantly, you can look at them for specific rows. And so when you put it in production, you might always want to see the confidence interval. So if you're doing, say, credit scoring, so deciding whether to give somebody a loan, you probably want to see not only what's their level of risk, but how confident are we? And if they want to borrow lots of money and we're not at all confident about our ability to predict whether they'll pay it back, we might want to give them a smaller loan.
Okay. Yes, probably banks use that, and that's pretty mean. Whatever. The thing that brought to my mind, which almost always they give this example of, like, a doctor giving treatment, like, confidence level better be high if the doctor is doing some invasive treatment or, like, God forbid, cancer related things. So yeah, that is something that will happen. AI is being used everywhere, so we better know what we're doing, because you definitely need a human in the loop. It's a scary world out there.
Okay, so those are the two ways in which you would use this. Okay, let me go to the next one, which is the most important.
What did we do here exactly? We summed up standard deviation, divided by summed up predictions, and sorted it. So saying, but we are not checking for the, is this like a confidence level-ish? We are not saying, like, we're not checking with how much data we have. I don't know if it matters, but it's a thing we could do, saying we have less data for this compared to this. Okay.
The most important is feature importance. And the only reason I didn't do this first is because I think the intuitive understanding of how to calculate confidence interval is the easiest one to understand intuitively. In fact, it's almost identical to something we've already calculated, right? But in terms of which one do I look at first in practice, I always look at this in practice. So when I'm working on whether it be...
Yes, we look at, but how do we know, does the random forest tell us? Because, like, knowing which feature is the most important is super useful. And like, I've used the website called Big ML, and they give you the, there's a word for it that I've forgotten, like impact, I don't know, something like that, like how important that feature, aka column, database people call it column, ML people call it feature, how much it impacts the prediction.
A Kaggle competition or a real world project, I build a random forest as fast as I can,
so that we can
try
analyze
and get
it
to the point that it's like.
Okay, so it's called feature importance. I don't know if it's called that in Big ML. It's a free website you can run. It's all like, it's a non-code, low-code website. It's definitely non-code. You just click buttons, and it trains models, does what is it called? Like training, splitting, and it has all types of models. It has like I learned the word ensemble there. No, not AutoML. It's called Big ML. It's a website. Big ML. I'm gonna say website. Oh God. Well, it's called Big ML, right? It's not. Yeah. See the green thing. It's a green thing. I suppose I can't use it, and it's free, even though it says that do the 14-day thing. But it's resource related. Like if you want to run, this brain is pretty. Can we just see? Yeah, there are videos. AutoML is the technique of training ML models without coding. Ah, I see. Got it. Yeah, I suppose it's called AutoML then. Thank you for the information. Yeah, probably then. It's that. Running things without coding, and it gives you visualizations. It gives you, you just have to have clean or useful or data that you understand enough. I actually learned the R squared, the mean squared error, stuff like that there. Not that I still know what they mean fully. Like I know, but each time I need a refresher. Each time because like I need to be confident when I say, oh, I know this thing. But if I don't, then how can I say I know it? So I recognize it is a better way.
Significantly better than random, but doesn't have to be much better than that. And then the next thing I do
Which one?
is to try and get it to the point that it's like, significantly better than random.
Yes, a good deja vu. That's basically all learning is for me. I never have. Yeah, literally. Yeah, I always say that. Learning in, uni college is you recognizing this stuff later on in life. Things shouldn't be new, foundational things. So that's all learning is for me. Maybe it's different for you. Maybe you can recognize and know things. But for me, it's mostly like when you face a problem and you're like, I know there's a thing called that could be the solution. And then you look for it. And that's called having experience, I think.
But doesn't have to be much better than that. And then the next thing I do is to plot the feature importance. And the feature importance tells us in this random forest.
So feature importance is an available tool that you can check for random forests. Coolsies.
Which columns mattered. Right? So we had like dozens and dozens of columns originally in this.
Oh look, enclosure was a column, was a feature. Oh shoot, you lost me. Why not? I can. Is there a way that I can? Let's do a BRB. Hi, I'm back. The emulator crashed no, actually the emulator didn't crash. The app crashed. It happens. It's life. No worries. Thank you. Oh, my hijab changed. The app crashed for some reason. Okay. Let's continue this way. We are talking about feature importance. So we see that the year made has the highest feature importance, which is like feels obvious because people care about buying new things. And the enclosure, which I think is the thing we looked at for large, mini stuff like that, has really not great impact.
This data set, and here I'm just picking out the top 10. So you can just call RF feature importance. Again, this is part of the fast.ai library. It's leveraging stuff that's in scikit-learn. Pass in the model. Pass in the data frame, because we need to know the names of columns, right? And it'll tell you, it'll order, gives you back a pandas data frame showing you in order of importance how important was each column. And here I'm just going to pick out the top 10.
Okay.
So we can then plot that, right? So fi, because it's a data frame, we can use data frame plotting commands. So here I've plotted all of the feature importances, right?
Visualizations are always cute, no matter how useful. Feature importance plotting. Let's look at our feature importance. Same. And then let's plot it. Fi is fast.ai, right? So fast.ai has its plotting library. Oh, that feels different. Why is his more smooth? Oh, wait, where's the names of the columns? Ah, legend false? Why? Is it column name or is it legend? Let me remove that. Actually, let me see what's in fast.ai plot. This method, we have kind line, subplot, layout, figure size, index use, title, grid. I like grid. Legend style, logx, font size, color map, sort column. Okay, that's some useful information and too much information, which we can read anytime. Whoa, okay. What was it that I wanted to try? Oh, grid. Grid, true. Does the true have to be true? There. Show me. Nice.
And so you can see here, and I haven't been able to write all of the names of the columns at the bottom, which that's not the important thing. The important thing is to see that some columns are really, really important, and most columns don't really matter.
Most don't matter.
At all. And like in nearly every data set you use in real life, this is what your feature importance is going to look like. It's going to say there's like a handful of columns that you care about. And this is why I always start here. Right? Because at this point, in terms of like looking into learning about this domain of heavy industrial equipment options, I only going to care about learning.
Yeah, it's feature engineering, isn't it?
Learning about the columns which matter. Right? So Are we going to bother learning about enclosure?
Nope.
Depends whether enclosure is important. And
it's not.
There it is. It's in the top 10. So we are going to have to learn about enclosure.
Oh, we have to? Yeah. Wait. So if it's showing up here, then it matters. Got it. But like maybe you don't have time and you're in a competition and you're like, you know what? Top 10 doesn't matter. Top 3 matters.
So then we could also plot this as a bar plot. Right? So you can hear I've just created a tiny little function here that's going to just plot my bars, and I'm just going to do it for the top 30. And so you can see the same basic shape here, and I can see there's my enclosure. Okay.
That's pretty important. Let's look at our bars. Did we run it? Yes, we did. Okay. Ooh, I love the colors. Year made is super important, and then after that we have coupler system, project size, and product classic description. I suppose description matters. And then these matter the same, almost. And then enclosure is right here. Oh my god, our importance is not even the same. That's really interesting. Like, look, the second one is almost right behind the first one, but for us it's like, I feel like saying it's a mile away, but I don't use miles, so it's a kilometer away. And then these three are like best friends, but not here. Very interesting.
So we're going to learn about how this is calculated in just a moment. But before we worry about how it's calculated, much more important is to know what to do with it. So the most important thing to do with it is to now sit down with your client or your data dictionary or whatever your source of information is, and say to them, okay, tell me about year made. What does that mean? Where does it come from? Plot lots of things like histograms of year made and scatter plots of year made against price, and learn everything you can, because year made and coupler system, they're the things that matter. Right? And what will often happen in real-world projects is that you'll sit with the client and you'll say, oh, it turns out the coupler system is the second most important thing. And then they might say, that makes no sense. Now, that doesn't mean that there's a problem with your model. It means there's a problem with their understanding of the data that they gave you. Right? So let me give you an example. I entered a Kaggle competition where the goal was to predict which applications for grants at a university would be successful. And I used this exact approach, and I discovered a number of columns which were almost entirely predictive of the dependent variable.
Can I give an example? Is it if the person is a male or a female? Not funny. Not funny at all.
And specifically, when I then looked to see in what way they're predictive, it turned out that whether they were missing or not was basically the only thing that mattered in this data set.
Whether data was provided or not?
And so later on, so I ended up winning that competition, and I think a lot of it was thanks to this insight, right? And so later on, I heard what had happened, and it turns out that at that university, there's an administrative burden to filling out the database. And so for a lot of the grant applications, they don't fill in the database for the folks whose applications weren't accepted, right? So in other words, these missing values in the data set were saying, okay, this grant wasn't accepted, because if it was accepted, then, the admin folks are going to go in and type in that information. So this is what we call data leakage. And data leakage means there's information in the data set that I was modeling with, which the university wouldn't have had in real life at the point in time they were making a decision, right? So when they're actually deciding, which grant applications should I prioritize?
Oh yeah, that's where I got it from, the CV thing, right? If your name was a man, you would got it. I actually read that very recently. Yeah, the Amazon CV thing. Yeah. Yep. Not fun at all. By the way, I'm gonna recommend this book that I recently started reading, which I've been really lazy on reading, but it's really fun. Whenever I read it, I'm actually motivated to read more, and it's nonfiction, which is unheard of. It's called The Alignment Problem, and it's written by the same guy. It's written in 2020, but the part that I'm reading right now is mostly history of like AI, machine learning. It's about how machine learning should care about what humans care about. That's basically what it means. Simply put, the alignment problem in the AI world is the question of how to create super intelligent or just AI that is friendly, helpful. And what I want to say is the guy who wrote the alignment problem is exactly the same guy who wrote Algorithms to Read By, which is also another popular book. No, wait, it's not the same guy? It is, right? Is it not? Why did I think... See, yes, they are. Then why was there a different name there? I saw Thomas something. Anyway, yeah. These two books. I've read the first one. I'm currently reading the second one. And that's where the guy is bringing up the Amazon issue. And other issues. Like it makes me... it feels weird to even just talk about it, but Google Photos had an issue with, not white people. I don't want to talk about it more. You can learn about it. And they made some drastic changes for that. And I'm sure you guys remember the part where, cameras couldn't recognize darker faces. Yeah, people of color, yeah. They were being tagged as not human. So that's messed up. That's some bad data. And it's always the problem with data. It's never the problem. I mean, it's biased data. It's biased data, not biased algorithms. Because algorithms do what we tell them to do. Data is the part where it's coming from humans. And we are really flawed. Yep.
Yes. They don't actually know which one.
Yeah. I see. Yeah, it's. I think. I don't know. I can't really say how. Is the democratize the correct word? Just more people being able to train models to become people who work on machine learning, things being more available, more accessible, means these issues, if they're not fixed, at least they're highlighted, they're not hidden, and people like you and me are not being discriminated against, right? Yeah, so people like you and me should take the stand and fix it for these people. No, I'm not saying that I can, but I'm just saying that we should be, as Hamilton says, in the room where it happens. Hamilton doesn't say it, but it's in the Hamilton musical. Okay. Yeah.
The admin staff are later on going to add information to because it turns out that they got accepted. See what I mean?
Yeah. Crowdsourcing, I suppose, even though crowdsourcing is, it's also it's super useful. I'm not saying I'm against it, but it's, no worries. But it's also people's efforts without paying them. I mean, I know sometimes they do these thank yous, which is really sweet of them, but I doubt crowdsourcing ever pays. At least Amazon's Mechanical Turk has some form of payment, no matter how small, Yeah. And I know like people enjoy seeing their names on the leaderboards, and crowdsource thing is fun, but it's still not the best way. It's a really good way, but not the best way. Not that I know what's the best way. I'm just here to critique, not to give solutions.
Admin staff are later on going to add information to because it turns out that they got accepted. You see what I mean? Right?
Mm-hmm.
So
that thing he's talking about is really interesting. The information leakage part, where the information is available after the fact, not while the decisions are being made.
One of the key things you'll find here is data leakage problems, and that's a serious problem that you need to deal with. The other thing that will happen is
I even received goodies from that program. Not sure if the collected data will be used in the future releases of AI, they claim though. Oh, they definitely will use it. They definitely will use it. I'm sure about that. Yes, and I won't tell you how sure I am or why I'm sure. Okay, bye. Yeah, it's nice. It's really nice. I also have acquaintances, I wouldn't call them friends, but people that I know who have also received like goodies, which is beautiful incentive. It's nice, but it's not sustainable for the people who are doing it. Like as a student, it's cool that you're doing that, and I know this is a rant that's starting. I know that volunteering is something that most people need on their CVs. It's something that's needed, but also it shouldn't be taking advantage of the person who needs it. I'm not saying Google is doing that. I'm just saying volunteering is a weird concept for people who are just students. And yes, they have free time and they have energy and maybe they like it. But it's a weird concept of using people's time and energy without paying them and saying, you're getting experience. Okay, great. I've done it. I think, yes, I have. Still, in this economy, money matters.
You'll often find it's signs of collinearity. And I think that's what's happened.
Sorry for the rant.
Here with coupler system. I think coupler system tells you whether or not a particular kind of heavy industrial equipment has a particular feature on it. Mm-hmm. But if it's not that kind of industrial equipment at all, it will be empty, it will be missing. And so coupler system is really telling you whether or not it's a certain class of heavy industrial equipment. Now this is not leakage, this is actual information you actually have at the right time. Yep. It's just that like interpreting it, you have to be careful. Okay? So I would go through at least the top 10 or like kind of look for where the natural breakpoints are and really study these things carefully. To make life easier for myself, what I tend to do is I try to throw some data away and see if that matters. So in this case, I have
data that's not a part of, not high in the future importance list, right? We can throw that away and maybe that will make our performance, maybe like the speed of the performance higher, because like when it comes no worries, just to be fair, swags were the last thing we got. We were offered free ML courses along the way. That's great. That way the most valuable thing, that's great. I had no information about that. Then that knowledge is like, it's something I'm happy that they're doing that. Honestly, I didn't know. Okay, I will be less mean now. So they're giving things that they can give, which is pretty good. I'm glad. Did you take any of the courses? Were they anything interesting? I'm guessing they were Google courses. That's cool.
Had a random forest which Let's go and see how accurate it was.
Oh, that's cool. That's amazing. Good job. So for the performance, having less data means it's faster, but there's also like the point of performance being less resource intensive, like not taking up too much resources. That's also something that should be considered, in my opinion, since like today's AI is just eating up GPUs. So less data, less resource in computation related things. These are important things to talk about when you have a model, I think.
0.889.
So that was
what I did was I said here, okay, well,
that was our first, that was before deleting columns features.
Let's go through our feature importance data frame and filter out those where the importance is greater than 0.005. Right, so 0.025, so 0.005 is about here, right? It's kind of like where they really flatten off. Right, so let's just keep those. And so that gives us a list of 25 column names.
I'm curious.
And so then I say, okay, let's now create a new data frame view, which just contains those 25 columns. Call split vals on it again, just put it into test and training set, and create a new random forest. And let's see what happens.
From 88 to 89.
And you can see here the R squared basically didn't change.
Oh, really?
891
88
versus 889. So it's actually increased a tiny bit.
It's not bad. Let's test it on mine because I know it's different. Keep. Based on our feature importance, we're getting less columns to keep. He got 25 to keep, I'm getting 23 to keep. And then we do the training, splitting first and then the training, and then we'll see our score. $89 versus, that's a long thing here. Oh, did I miss it? Nope. Oh my god. Wait, where is it? Do we not have it here? How to find out how many features scoop. Okay. I'll let you know after I check my score. What happened to my previous score? Did I just jump through it? Okay. I don't know what happened to my score. Maybe he's talking about lesson 1 score? Is he? I don't know. Okay. The album method used in k-means clustering to find best features. I'm not sure what you mean by the album method, but are we talking about like the hockey stick thing? So we have the feature importance, right? And we have a value for them. Like you even saw it in the table up there, which I'm not gonna go back up. It's a long way up. But here we have I guess this is our model, the FI, and we're saying filter by where the feature importance is over 0.005, so that's just a number that he chose, and we're checking the length, which is how many features are left. So this is what he decided, based on the feature importance. And then he made a copy, did the training and split the training and validation, and then ran it again. Lower limit that we just chose for no reason, but also some reason. By the way, for the album method, I'm not sure what you mean. So If you let me know, I would be grateful. Just a small, nothing too much writing on your side. Just whether it's a convention or whether it's something that we just decided, I'm not sure.
Right. I mean, generally speaking, removing redundant columns, it shouldn't make it worse. If it makes it worse, they weren't redundant after all. It might make it a little better, because if you think about how we built these trees.
NK means cluster. Yes, I know what K means clustering is, but I just know that doesn't mean I can tell you what it is. I recognize it. We have to choose I think there are dots. I don't know whether you wrote them or whether they're already there. With the K. Denoting the number of clusters. A neat technique to find the best K value is to try just try as many and then choose the best one. That's also like a style of ensemble, isn't it? But like in a different way. No, wait, that's not true. Ensemble is averaging out in a way. Yours is choosing it. We should see like an so you call that an elbow. I've heard it being called the hockey stick, like plot or something. Not a plot, but diagram. I don't know. Oh wait, am I wrong? Yours is the correct way of saying it. See, like this. But the other way around, maybe. Yeah. Maximizing distance between clusters and minimizing distance between the members within the same cluster. Okay, so yours is an elbow. Let me look at. Can I say elbow method? Oh wow, it is a thing. Oh, it does look like an elbow. Yeah, I guess there are different ways, but yours is like almost like an elbow. It's not a hockey stick. So like the elbow point is maximizing distance between clusters and minimizing distance between the members within the there are no dabbing. There is one. I've seen it. There definitely was one. Maybe they removed it. Oh, there. Found it. Okay. I learned about the elbow method. That's cool.
When it's deciding what to split on, it's got less things to have to worry about trying. It's less often going to like accidentally find a crappy column. So it's got a slightly better opportunity to create a slightly better tree with slightly less data, but it's it's not going to change it by much. But it's going to make it a bit faster, and it's going to let us focus on what matters. So if I rerun
faster, that's the reason it makes it faster.
Feature importance now, I've now got 25. Now the key thing that's happened is that when you remove redundant columns, is that you're also removing sources of collinearity, right? In other words, two columns that might be related to each other.
Okay.
Now, collinearity doesn't make your random forest less predictive, but if you have two columns that are related to each other, this column's a little bit related to this column, and this column's a strong driver of the dependent variable, then what's going to happen is that the importance is going to end up like kind of split between the two collinear columns. It's going to say like, well, both of those columns matter, so it's going to split it between the two.
Can we check for that?
So by removing some of those columns with very little impact, it makes your feature importance plot clearer. And so you can see here actually.
Wait. Why? I see the thing that I was talking about, the three ones being here, but mine was like that before I removed the columns. Can I do the plot and see again? Did nothing change for me? Tire size? No, it did. Tire size is here, but here it's here. Like I could see the collinearity. I learned that word just now. Up here, and now they're still friends, but they're like moving on, you know?
Year made was pretty close to coupler system before, but there must have been a bunch of things that were collinear with year made, which makes perfect sense, right? Like old industrial equipment wouldn't have had a bunch of kind of technical features that new ones would, for example. So it's actually saying like, oh, okay, year made really
more
matters,
important now.
right? So I trust this feature importance better. You know, the predictive accuracy of the model is a tiny bit better, but this feature importance has a lot less collinearity to confuse us.
So collinearity could confuse us. Okay.
So let's talk about how this works. And it's actually really simple. And not only is it really simple, it's a technique you can use not just for random forests, but for basically any kind of machine learning model. And interestingly, almost no one knows that. Like many people will tell you, oh, this particular kind of model, there's no way of like interpreting it. And the most important interpretation of a model is knowing like which things are important. And that's almost certainly not going to be true, because this technique I'm going to teach you actually works for any kind of model.
Okay.
So here's what we're going to do. We're going to take our data set, the bulldozers, right? And we've got this column which we're trying to predict, right? Which is price.
Sales price.
And then we've got all of our independent variables. Okay, so here's an independent variable here, year made. Right, plus a whole bunch of other variables. And remember we had, after we did a bit of trimming, we had 25 independent variables.
I have 23 left.
Okay. How do we figure out how important year made is? Well, we've got our whole random forest, right? And we can find out our predictive accuracy. So we're going to put all of these rows through our random forest. And we're going to spit out some predictions.
Yes.
Right? And we're going to compare them to the actual price. You get, in this case, for example, our root mean squared error and our R squared. And we're going to call that, like, that's our starting point, right? So now, let's do exactly the same thing, but let's take the year made column and randomly shuffle it. So randomly permute just that column. So now, year made...
We're messing with, I mean, it's obviously going to be a copy of the data, but we're messing with the data?
Has exactly the same like distribution as before, same mean, standard deviation, but it's going to have no relationship to the dependent variable at all, because we totally randomly reordered it.
Yes! So, this is haram. What is he doing?
Before, we might have found our R squared was 0.89, right? And then after we shuffle...
I think he's searching for the second most important feature, maybe? I don't know. Let's see. And because like there isn't much time left, we have 4 minutes left. I'm like scared. Astaghfirullah.
Year made. We check again, and now it's like 0.8. Like, oh, our score got much worse when we destroyed that variable. And it's like, okay, let's try again. Let's put year made back to how it was. And this time, let's take enclosure and shuffle that. Right? And we find this time with enclosure, it's 0.84.
Which is good.
And we can say, oh, okay, so the amount of decrease in our score for year made was 0.09, and the amount of decrease in our score for enclosure was 0.05. Right? And this is going to give us our feature importances for each one of our columns.
So if the model doesn't give us feature importance, we can make it ourselves. Is that what he's saying? Because I think, I don't know. I have no idea. To avoid overfitting maybe, depending on a few features and totally ignoring the remaining despite their importance. Maybe. Could be, yeah.
Yes.
Wouldn't just excluding, let's say,
Yeah, excluding would work better. Just deleting it.
each column and running a random forest and checking the decay in the performance.
Yeah, so
good point.
You could remove the column and train a whole new random forest, but that's going to be really slow.
Ah, so that's for to save time. Interesting.
Whereas this way, we can keep our random forest and just test the predictive accuracy of it again. Right, so this is nice and fast by comparison. In this case, we just have to rerun every row forward.
Good points on each side. Everybody has points.
Forward through the
10 points to Gryffindor.
Forest for each shuffled column.
I see. We're just basically doing predictions after
Exactly.
shuffling. Okay.
Yeah, great question.
So if you want to do like multi-collinearity, would you do 2 of them and then random shuffle and then 3 of them random shuffle? Like that?
Yeah, so I mean, I don't think you mean multicollinearity. I think you mean looking for interaction effects. Yeah, so if you want to say which pairs of variables are most important, you could do exactly the same thing, each pair in turn. In practice, there are better ways to do that because that's obviously computationally pretty expensive. And so we'll try and find time to do that if we can. Okay, so
Time's up.
We now have a model which is a little bit more accurate and we've learned a lot more about it. So we're out of time, and so what I would suggest you try doing now, before the next class, for this bulldozers data set, is like...
Not gonna do it, but tell me.
Go through the top, I don't know, 5 or 10 predictors, and try and learn what you can about how to draw plots in pandas, and try to come back with like some insights about like what's the relationship between year made and the dependent variable, what's
We did that for the enclosure one.
the histogram.
So like it's doable. We have the code, I can copy and paste it. Next time maybe?
Of year made, try and find, some possible, like, now that you know year made's really important, is there some noise in that column which we could fix? Are there some weird encodings in that column that we could fix? This idea I had that maybe coupled system is there entirely because it's collinear with something else. Do you want to like try and figure out whether that's true? If so, how would you do it? FI product class desk, that rings alarm bells for me. It sounds like it might be a high cardinality categorical variable.
Isn't it a description?
Might be something with lots and lots of levels because it sounds like it's like a model name. So like go and have a look at that model name. Does it have some ordering to it? Could you make it an ordinal variable to make it better? Does it have some kind of hierarchical structure in the string
Order.
that we could split it on like hyphen to create more subcolumns?
Using pandas profiling for many of these graphs an easy task. I don't have information, but I can look at it.
Have a think about this, and so try and make it so that, by Tuesday when you come back, you've got some new, ideally you've got a better accuracy than what I just showed because you've found some new insights, or at least that you can tell the class about some things you've learnt about how heavy industrial equipment options work in practice.
Cute.
Okay? Great. See you on Tuesday.
So the class is about all the streaming things. Heavy industrial pandas profiling. Installing examples. Huh? What happened? It's deprecated. Who killed it? Exploratory data analytics with pandas profiling. A picture is worth 1,000 words. Oh, that's pretty. Wait. Really? it's like, it has like, yeah, exploratory data analytics. Just throw the data at it. Oh, that's it. I probably need to install it. Let's we probably should do this like with a raw, with our, wow, as easy as that. What happened? Why is adding one line of code here, but also putting it behind this, which is, yeah, that's fine. DF raw means everything, doesn't it? Which we shouldn't really look at everything. We should look at our training, raw train. Yeah, I'd rather look at raw train. Oh, what did I copy? Copy. Hey, what is happening? What did I do? God, what was that? Fine. We're not using pip here, are we? We have we have pandas summary, which, yeah. Let me try this part, and if it gives me errors, then I will do the install. Yeah, okay, fine. Error. Expected. Can I use this? I should be able to use that, right? Ya Allah. No. Yes. Okay. No. God. You're saying do this, but have a space? It's that, not the other thing? We're using shell. Thank you. I thought it's the other thing. Our pip is not upgraded. Thank you. Okay. Face tracking is still there. I thought it's gone because I'm like too seriously into whatever it is I'm doing here. Ooh, it actually worked. It ran. Now I can do this right here. Yeah, okay. It's just the warnings. Always ignore them. That's the best thing about warnings. We have a thing called raw train, I think, and that's what I plan on using for now, not the whole. And actually I might be wrong by using that, but let's try. Like maybe, because I think I'm giving it like the raw data, just the table, not a model, because we haven't run the model, and I think that should be the case. I'm looking forward to this. Take your sweet time. I still can't believe I'm 3 lessons in. What's next? Feature importance, tree interpreter. Okay, we're learning about trees. Still random forests, data product, and live coding. Cool. And then still random forests, and then gradient descent. Gradient descent and logistic regression, regularization, learning rates, and NLP. What? More NLP and columnar data. I don't know what that is. Embeddings, which is still NLP, and ethical issues. Ooh. You can also display the report in the notebook the way you used generate a report. Yes. I see the out. Oops. Sure. Don't give us the output file then. keep the momentum. Okay, so this guy is giving us a report, but I think in his other to notebook iframe. Got it. Instead of to file, we say to note. Can you not you. To notebook something. I'm gonna say pandas profiling something. I mean, no, it's fine. Okay, pandas profiling to notebook. Just give me the code. Maybe the name of the parameter changed. Check the resource. Oh, cool. What should I check? Should I check this? Will I? Or should I check? Because that one I don't have problems, but output file. No, the error that I got had to do with the folder not existing, I think. Let me see if I can find the to notebook thing first. Somebody give me the answer right away, please. Don't make me look for it. To notebook. It's called to notebook. Notebook. Nope, not here. I see this guy using it. See, to notebook _ iframe. There, I'm gonna do that. Okay, let's try. _ iframe and then that. I definitely should not train it again, because it took time. So I'm gonna add another line of code and see if this allows me to do it. Nope. Okay, then I need to run it again. To file, but why? Sorry. Yeah, YouTube doesn't allow them, I think. But why should I do to file? I want to see it right here. Has no... Really? Sorry. Profile. In case you wanted to export. Yes, you're right. Open in a new tab. Can I pause this? Darn it. That wasn't the intention. What happened? There. He's saying to notebook iframe. That's what he's using. You can check by clicking this link. Do you have the code? Maybe you do. Okay. We have profile and then for output. By the way, now it's called Y data profiling. So I think I'm gonna try using that because apparently the other one is deprecated. So if I go back up, I should use this. Which means I should install you. Okay. Cool. And then I should run you. What do you mean? Fine. Don't want it. Sorry. Okay. ChatGPT can help in these situations. Provide the version that tell you how to. I agree with you. but stay there. Okay. How can one minimize this? Oh, like this. Wow. Okay, I'm gonna run this profile report, and then does it make sense for me to question mark my object? I know I shouldn't run it yet, but I actually have ChatGPT, so we can ask ChatGPT. The thing is, I had this this other one that was super long, like down here. Even this one, I was like, ugh, I have to scroll each time. But now I realize I can make it smaller. Oh, look, we have this. So we have methods. We have to file, to HTML. That's all we have. The other one apparently doesn't exist. And if I do it 2 question marks, we have what's inside there. Got it. Okay, 1 question mark is the one that I needed. Try 2 widget instead of 2 notebook. But is it available there? Not. I'm gonna go for 2 HTML and hope that it will like give it to me here instead of nope. Beautiful. It depends on the version, most likely, but I didn't like ask for any version. To file. For to file, do I have to give it the path? Otherwise it will be mad at me? Or will it... What is this? Should I? Maybe version. Constance should have the version. Okay. Sure. That's my report. There was something that I needed to check. Oh, what? There. Sorry. sorry. Okay. There. Okay. Now we can see the file thing. So, number of variables, 65. Number of observations, I think this is observations means rows. Number of missing, 43%. Look at that. Size, variable types, categorical. That's a lot. Date, we have a date actually, but I guess it didn't recognize it. Percentage of missing values. Would you look at that? This is amazing. The profiling thing, like wow. Rows, records, instances. Got it. And now each of them, but with more information. None or unspecified. And this is a Boolean. Missing way too much. Toggle details. In which way? So thank you. The missing data is a lot. The data sets are not parsed yet. Dates, sorry. Hello. This is why they're considered a string for now. I think if we had told it it's dated, it would have gotten it, so the type isn't there. Your name is Bumyu? Or is there another name you want us to call you by? And hello. We are looking at... So, if you want me to update you, we finished lesson 3 of fast.ai's machine learning for coders. and we're just looking at our data to understand. We're profiling our data. I'm good cop. You guys can be bad cop for our data. It's fine if things are missing, no worries. Coupler system was a high importance thing. Do we really have that much missing data? Is there a way for me to look at it? Oh, enclosure. Oh my god, look at that enclosure with the thing. These are like categories. That's why the guy said I don't understand, because it was just categories within a table, so it doesn't really matter. And the missing percent is 0.1, which is amazing. Forks. Where is the year made? Machine ID, model ID. I feel like model ID should be important, and we have 0% of 0 data. That's pretty cool. Where's the year? Sell price is good, but that's our target, so we shouldn't. Thumb? What's a thumb? Year made. There it is. Mean is 1897. Wow. Minimum is 1,000. That is a lie. That is a lie. Don't you think? It doesn't make sense. Ooh. Look at that. Look at this. Look at that. Oh my god. Minimum 5th percentile Q1. Okay, that's fair. And like maximum is 2012. What's mad? Outliers. I see outliers here. We have extreme values, which is really cool. We have 1,000. This has to be like null or something. Why 1,000? That makes no sense. Like 1919. Okay, fine. People made cars then, or trucks or whatever, but not in thousands. I'm very sure about that. So yes. And then the 5 max values. But like the fact that we have 9% of our data where the year is 1,000, that's wrong. Histogram. See? Like everything is in the 1900s and 2000s, and then we have year 1000. Shut up. What else do we have? This is really cool. Like, I had no idea about this, and everything is just here. What are these correlated? I think we created this, didn't we? Or maybe it was already there, I don't remember. This variable is highly correlated, correlation 99. So like, because it's super correlated, it doesn't matter in a way. Sale month, constant should be ignored. Okay, whatever you say. This is pretty. What's a Pearson? Correlation. The dates are super correlated. Sale elapsed, sale year, fair. Maybe they have a naive business rule to replacing missing year with that. Yeah, that's what it looks like. It's probably like their null values, but that's not. Different types of correlations. Yes, I see them. So there are different types of correlations. I don't know what that means, but these look pretty similar to me. No, there are less similarities here. Sample. This was beautiful. Thank you. Okay, homework done. Now we can profile our data. That's very cool. Okay. This time How long have you been streaming? Wow, 2 hours. Okay, no worries. It's a weekend day. I still have time because I have a lot of other personal things to do, but there's still time. Weekend's just getting started. I am still processing the information learned. This was really fun. We learned about feature importance. We learned about messing with data, which is still, I'm gonna have nightmares about that. Yes, today was a nice day. Thank you for all the information, for the chat, for accusing me of being AI. We learned about elbows. I feel like Dora right now. What was your favorite part of the stream? Yes, it was fun. My favorite part was when I got accused of being AI, and that was fun. But also, I really like how the students ask questions and they're just plucking them from my... cool. That's nice. Yes. For the books, I mostly listen to books instead of reading them by eyes. But the alignment problem one, I got it as a gift, so I have the physical. Yes. I have the physical book, but Algorithms to Live By, I listened to that one, and it's very interesting. It's surprisingly interesting because, like, it's about using algorithms in your daily life to make decisions and choices. Yes. Okay. I should be going and you guys should live your life. So thank you for learning with me. I hope we can continue. Oh, thanks. You're really kind. Yes, you can listen to them or watch them in 2x level because that's what I mostly do, but you can't 2x streams that are live. Bias in AI. Oh my god, we did, didn't we? That was scary. Yeah, he talked about data leaking, but then we talked about bias in AI in our part. So Bomu, I'd like to, if you can give me information about yourself, because it's cool, but you don't have to. Mostly, like, are you a student? Like, are you interested in learning ML, for what reason, and things like that. True, yeah, because I learned about the both Amazon CV thing and the Google Photos issue thing in that book, both of them. Yeah. I think I don't think I'd heard it like with that much detail described elsewhere, but it's common knowledge enough, I think, the Amazon CV thing. Yep. Okay. Alright, sorry, brain freeze. Alright, thanks for being here. I hope we can learn more together. You're an intern right now at a startup company, very new to data science world. Cool. That's fun. I hope we can learn things together. This course is called Machine Learning for Coders, so I feel like people with coding background will like have a better time understanding these things. 'Cause like I mostly am scared learning about these things, even though I've worked as a software engineer before. But they're not, I don't know, they're not always super friendly, you know, they sound scary for me anyway. So I took data science course this year, pretty recently. I think it ended in July. So that gave me the confidence to take this course, which is like, you can understand my confidence level. It's almost always low. Yeah, so I hope we can learn things together. And if you guys have questions, honestly, let me know. I don't mind. That doesn't mean I can give you answers, but based on my experience, I can give you answers as like bigger sister. Yeah, my Twitter's up there, right there. And I'll probably be back with more streams starting tomorrow. Okay, thank you. I don't have anything else to say, so I should go and do the things that I'm supposed to do, which is some part of it is resting, other parts is actual things, some emails. Thank you, bye-bye. I will end the stream starting from 5, 4, 3, 2. Thank you for your time and thank you for being here. Goodbye. Yep, countdown time. 1 and then 0. Lift off. Goodbye.